Section: Introduction. In this section, we introduce a learning system architecture called memory mosaics. Memory mosaics use multiple associative memories to perform prediction tasks. These systems are similar to memory networks and transformers but have some key differences. Memory mosaics have disentanglement and compositional capabilities like transformers, but their internal workings are easier to understand. Our work makes three main contributions. A. Recognizing the similarity between smoothing associative memories and self-attention. B. Introducing the predictive disentanglement principle, which explains how training breaks down tasks in interesting ways. C. Demonstrating that this transparent architecture matches the performance of decoding transformers in language modeling tasks. We describe the basic architecture, explain the predictive disentanglement principle, extend these ideas to fully formed memory mosaics, and present results from medium-scale language modeling experiments. An associative memory stores key value pairs and retrieves values based on a given key. We represent this retrieval process as a function of the queried key and all stored pairs. Associative memories do not consider the temporal order of pairs, making the retrieval function invariant to permutations. This property allows us to view an associative memory as estimating a conditional probability distribution based on the stored pairs. To predict with associative memories, we use past observations to predict future ones. Each memory unit consists of an associative memory and a feature extractor that computes keys and values. The keys are based on past observations, while the values can depend on future observations. The memory retrieves an estimate of the unknown value by querying the key. Training networks of memory units involves deep networks with glue layers and elementary memory units. By unrolling the network in time and back propagating gradients, we can train the network effectively. This process resembles masked self-attention but with some differences, such as the need for future time steps to compute values and the absence of position encoding. Each memory unit's output can be interpreted as predicting the unknown quantity based on past observations. Section Summary. In this section, we introduce a learning system architecture called memory mosaics, which utilizes multiple associative memories to perform prediction tasks. These systems, akin to memory networks and transformers, exhibit disentanglement and compositional capabilities transparently. Our work highlights the similarities between smoothing associative memories and self-attention, introduces the predictive disentanglement principle, and demonstrates that this architecture matches decoding transformers' performance in language modeling tasks. Section: Learning and Meta-Learning. In this section, we explore the concepts of learning and meta-learning. We consider a training process that can be seen as a meta-learning procedure, different from the learning that happens during inference when new information is stored in memories. By unfolding the network over a full input sequence, we can observe how memories operate. The training process aims to promote efficient memories that can provide accurate value estimates with minimal storage of key value pairs. Initially, assuming each memory unit has a fixed value extraction function, we can enhance the efficiency of each memory unit by adjusting the parameters of the key extraction function. This involves learning how to compare the current prediction context with past contexts to improve memory efficiency. By constructing keys that capture relevant information and adjusting the kernel bandwidth, we can optimize memory performance. When multiple memory units are available, the training process can also optimize the value extraction functions, distributing the prediction work among the memory units effectively. This redistribution not only enhances memory efficiency but also breaks down the original prediction problem into smaller subproblems that can be recombined in various ways. We discuss the concept of predictive disentanglement, where training a network of memory units is a meta-training process that learns to utilize memory units efficiently for the task at hand. Using multiple memory units proves beneficial when the overall prediction task can be divided into smaller tasks that can be predicted more efficiently independently. The disentangled memories can then be combined to make predictions for diverse inputs based on individually predictable components. To illustrate this, we present a scenario involving 3 moons orbiting a planet, where astronomers debate the best approach to predict future moon positions. One proposes a single table for all moons, while the other suggests separate tables for each moon, highlighting the benefits of independent predictions. In our model, each observation encodes the positions of the moons, and we consider 2 models with different numbers of memory units. By adjusting the key and value extraction functions, along with a combining matrix, we aim to predict future positions accurately. Setting specific matrices to identity yields optimal predictions after sufficient training data is seen. Section Summary. In this section, we explore the concept of learning and meta-learning in the context of training a network of memory units. We delve into how the training process optimizes memory efficiency by adjusting key extraction functions and redistributing prediction tasks among memory units. Through predictive disentanglement, we demonstrate how multiple memory units can be leveraged to address complex prediction tasks by breaking them down into elementary subproblems that can later be combined in various ways. Section: Training. In this section, we train the networks using randomly generated sequences of length 800. Each sequence contains 3 moons with related periods, ensuring at least 3 full periods of the moon system. Validation sequences are created similarly but with different moon periods. We analyze the prediction errors of both networks based on the context length, which is the number of observations stored in memory. For each sequence and time index, we calculate the average deviation between the true moon positions and the auto-regressive predictions. The plots display the error curves averaged over 512 sequences with the same moon periods from either the training or validation set. In the single-head network, there is a clear change in prediction accuracy after a full set of moon configurations is stored in memory. Before this point, predictions are based on the last observation, while after, predictions match moon configurations in memory. For the 3-heads network, the error curve improves after memorizing the orbits of all moons. Accurate predictions are made based on the slowest moon's period, even before the combined period of all moons. The weight matrices learned by the network successfully separate the 3 moons and combine individual predictions. Training the 3-heads network is challenging, similar to early XOR networks. We use smaller matrices and clip the loss to ensure convergence. Setting certain parameters to identity could bias the network but might aid in disentanglement. Complex networks of memory units are needed for more complex planetary systems. Persistent knowledge, stored in network parameters, is crucial for predicting future skies in different planetary systems. Nonlinear computations may be necessary to encode this knowledge effectively. Persistent memories store associative key-value pairs determined during training and remain fixed during inference. Interleaving contextual and persistent memory units increases the network's complexity. The output of persistent memory units represents the conditional expectation of an implicit value function, which becomes clear after training. Section Summary. In this section, we train neural networks using randomly generated sequences of moon positions, ensuring the sequences contain multiple full moon periods. We analyze prediction errors based on the context length stored in memories, observing improved accuracy when the networks memorize specific moon configurations. By disentangling moon predictions and recombining them, the networks successfully make accurate predictions even for different moon configurations, showcasing the importance of persistent knowledge in training complex memory units for celestial body prediction. Section: Routing. In this section, we explore how astronomers can predict the skies of a new planetary system by designing solutions using memory units and routing circuits. We start by tabulating the positions of the Sun, planets relative to the Sun, and moons relative to their planets. To achieve this, memory units need to compute these positions and route information between them. For static routing circuits, we use feature extractors and combining layers in memory units to determine routes during training. To enable dynamic routing, contextual memory units are introduced to adjust routes based on new observations. By updating contextual memory units at inference time, we can create new routes for each new sequence of observations. The division of labor among contextual memory units follows the predictive disentanglement principle, where memory units specialize in memorizing specific information independently. This principle guides the network to not only memorize fragmented information but also understand how these fragments connect and can be recombined in various ways, forming what we call memory mosaics. Memory mosaics, resembling transformers, excel in tasks like language modeling. Predictive disentanglement is crucial in language modeling, as predicting aspects like speaker identity or language can be done independently. By disentangling predictions, we can leverage more training data for better performance. We demonstrate the effectiveness of memory mosaics in language modeling using the TINYSTORIES dataset. By training a small language model on simple stories, we achieve better language quality and narrative consistency compared to larger models trained on generic web data. Our experiments involve a memory mosaic architecture similar to GPT-2 Small, with differences in positional encoding, attention mechanisms, and memory unit structures. Overall, memory mosaics offer a promising approach for tasks like predicting planetary systems and language modeling, showcasing their adaptability and efficiency in handling complex information. Section Summary. In this section, we explore how astronomers can predict the skies of new planetary systems by designing solutions that involve tabulating the positions of the Sun, planets, and moons. By utilizing a network of memory units that implement static and dynamic routing circuits, we can create memory mosaics that disentangle and recombine information, similar to transformers, to enhance language modeling tasks like predicting dialogues and generating story continuations with improved quality and consistency. Our experiments showcase how a memory mosaic architecture, resembling GPT-2 small transformers but with unique features like contextual memory units and persistent memory units, can outperform larger models in generating coherent narratives, as demonstrated with the TINYSTORIES and BABISTORIES datasets. Section: Training and Validation. In this section, we examine the training and validation performance of transformers and memory mosaics on BABISTORIES. We observe that memory mosaics slightly outperform transformers for shallow networks, but as the depth increases, both models show similar training and validation losses. It is important to note that the hyperparameters were initially tuned for transformers and then directly transferred to memory mosaics, which may explain the close tracking of training curves and put memory mosaics at a slight disadvantage in this comparison. To evaluate the quality of text generated by models trained on short stories, we created 24 prompts that test factual, logical, and consistency aspects of the generated continuations. Comparing the responses from a transformer and a memory mosaic, both with 18 blocks, we find that both models perform similarly on this task. Moving on to out-of-distribution evaluation, we explore predicting articles from simple English Wikipedia using models trained on BABISTORIES. Simple English Wikipedia articles are more complex and longer than BABISTORIES, presenting a challenging task. When analyzing the per-token average loss concerning the position of the generated token in the input window, we observe that memory mosaics, with 512 blocks, outperform transformers after around 50 tokens, indicating better in-context learning capabilities. For in-context learning evaluation, we utilize the REGBENCH benchmark to compare different architectures' abilities. By training on various artificial languages and evaluating on predicting the last token of test sequences, memory mosaics consistently outperform transformers, recurrent neural networks, and state space models across different training set sizes. Investigating attention differences between memory mosaics and transformers, we find that memory mosaics exhibit more consistent attention patterns, especially in longer contexts, compared to transformers using different attention mechanisms like rope and alibi. In conclusion, memory mosaics offer a promising alternative to transformers, showcasing strong memorization capabilities and potential for compositional learning systems. They provide insights into memory hierarchies and efficient knowledge memorization strategies, opening up new avenues for research and engineering advancements in artificial intelligence systems. Section Summary. In this section, we compare the training and validation performance of transformers and memory mosaics on BABISTORIES, finding that memory mosaics slightly outperform transformers for shallow networks but perform similarly for deeper networks. We also evaluate the quality of text generated by both models on various prompts and observe that they perform comparably. Additionally, we conduct out-of-distribution evaluations on simple English Wikipedia articles, where memory mosaics show superior performance in predicting tokens within larger context windows compared to transformers. Section: Acknowledgements. In this section, we acknowledge that JZ and LB were supported in part by the CIFAR Learning in Machines and Brains program.